Okay, now I'm looking at problem 2 of quiz 2b. In this situation, I give you two waves. These waves are basically pictures of waves on an ocean taken at different times. One at time equals 0 seconds, one at time equals 4 seconds. I also showed two buoys on the waves, and the buoys are just moving up and down. And when I say the waves are moving to the left. We have one question: what is the velocity of our waves? Okay, let's try to figure out everything we need to know. All the variables associated with this wave are amplitude, wavelength, velocity, and period. We know there's a relationship where the velocity is equal to the wavelength over the period. What can we determine just by looking at this graph? Well, first of all, we can determine the amplitude. I tell you at time equals 0, buoy A is 2 meters above buoy B. And so I'm telling you right there that the amplitude is equal to 2 meters. At time 4 seconds, buoy A is 2 meters below buoy B. And that's because A moved down and B moved up as the waves moved underneath them. So the amplitude is 2 meters. What about wavelength? Can we figure that out? Now, I already just drew in all these numbers, but the information I gave you is that buoy A is 6 meters to the left of buoy B. Since there are two tick marks there, I know the distance between each tick mark is 3 meters. And so I started by labeling this x-axis. So I started at the axis, or the origin, called that 0 meters, and then every tick mark I added 3 meters to determine what that axis looks like. The wavelength is the distance between here and for it to go between an entire cycle. Or you could choose a peak at 6 meters, go up to 30 meters. It's the same length. That length is 24 meters. And I can figure that out just by looking at the graph and labeling the axes. Now we have velocity and period. It'll be easiest in this case just to determine the velocity and then to use this equation to find the period. Let me show you why. I tell you that the waves are moving to the left. What that means, if I take some wave crest at time 0, at time 4 seconds, this crest has moved somewhere in that direction. I suggest you choose this as being the crest that it moved to. It's possible that these waves are moving really quickly and that this crest actually corresponds to this crest right here. You could have done that and you could still receive full credit, but since I didn't specify exactly which crests coincided, choose the easiest situation. We'll say that this crest moved to this situation between 0 seconds and 4 seconds. So now we could determine the velocity. How far did this crest move? It moved 6 meters. And how much time did it take to move 6 meters? Well, we have the times right there. It took 4 seconds to move those 6 meters. So the velocity is 3/2 meters per second. Now we have enough information to solve for the period. Velocity, which is 3/2, equals the wavelength, 24, over the period. Or we can multiply it by t, divide by 3/2, and we have 24 over 3/2 equals the period. This is equal to 24 times 2/3. I suggest you don't divide by a fraction because you're going to put that into your calculator wrong. Always just inverse the fraction and multiply by that. So this is equal to 48 over 3. That's equal to 16 seconds. Good. We've determined this information. We also answered the question 1, which is the velocity. It's 3/2 meters per second. Let's make sure we know what the second question is. What is the equation describing the motion of this wave? We're not worried about B or A. We're describing the entire wave. We want to know the displacement as a function of position and of time. We have a general equation for this. So let's write out the general equation. It's equal to A cosine 2 pi over the period. No, let's do it over the wavelength times x minus or plus 2 pi over the period times t plus our phase constant. This is our general equation, but we need to fill out everything except for the variables. We want this to be just a function of y, x, and t. Also, this minus or plus, this indicates the direction that the wave moves with time. That's why when I started to write period here, I'm like, no, I don't want to do that yet because I want to have the option of choosing a minus or a plus in front of it to say which direction the wave is moving. Since our wave is moving to the left, we know that corresponds to a plus. I suggest you just memorize that, but if you really want to work it out, you'd have to do a simpler situation and mathematically make sense of it. Now let's plug in everything that we know. Y is equal to A, amplitude is 2 meters, cosine 2 pi over wavelength, which is 24 meters, times x, plus 2 pi over the period, which is 16 seconds, times t, plus our phase constant. Okay, so I figured out all of our constants except for the phase constant. We need to determine what that is. The way to determine that is plug in any point where we know the time, x, and y. I say any point, but I suggest you always choose a maximum or a minimum position, because when we choose a maximum or a minimum, we know what the total phase is going to be. That is, I know that at a maximum, cosine of whatever this is going to be equal to the maximum. Therefore, this argument has to be equal to 0, or some multiple of 2 pi. If it's a minimum, then I want this argument, the total phase, to be pi, because cosine of pi will give us a minimum value. So let's choose the position of the buoy right there, B, at time 0. I can just as well choose the position of buoy A at time t equals 4 seconds, because that'll be a minimum. Either way, I'm going to get the same phase constant. Let's choose the simplest one we can, and this will be simple because we have time equal to 0, which will get rid of one of our terms. So at this situation, B at time equals 0, what is y? Y is equal to -2, and what is x? X is 18, because that's the position of buoy B. That is, I know that these set of variables correspond with each other. I can plug all these variables in, and the only other thing I'll have to solve for is the phase constant. Let's do that. -2 equals 2 cosine 2 pi over 24 times x, which is 18, plus 2 pi over 16 times time, which is 0, plus my phase constant, which is what I'm solving for. Let's divide both sides by 2, and what we get is this cosine is equal to -1. That means this argument is equal to pi, or 3 pi, or 5 pi, or 7 pi, but we'll make it simple. We'll choose just pi. 2 pi over 24 times 18 plus 0 plus our phase constant is equal to pi. 18 times 2 is 36. 36 divided by 24 is, let's divide them each by 3, and we get 12 over 24 divided by 3 is 8. Good, we can divide that even further. Divide it by 4, and we get 3 over 2. That makes sense. We divide both of those by 12. So 3 over 2 pi plus our phase constant equals pi. Let's subtract 3 over 2 pi from each side. We get phase constant is equal to -pi over 2. This makes sense to me, and the reason it makes sense to me is this looks like a cosine graph that's been shifted to the right by pi over 2. And when we have a phase constant of -pi over 2, we're taking our cosine graph, which typically starts at a maximum, and we're shifting it by pi over 2. And so our final equation to describe this graph is this. Minus pi over 2 is what our phase constant is. We solved for it. Okay, the final question says, graph the position of buoy B versus time. This is pretty easy. We're going to graph the displacement versus time. So the origin corresponds to time equals 0. Where is buoy B at time equals 0? Well, this entire graph is time equals 0, and we see buoy B is down here at a minimum at minus 2 meters. That's all I need to graph this, because I can go ahead and just draw a cosine graph. It's going to follow simple harmonic motion. What is the period of its movement? Well, I already told you the period. That's 16 seconds. Does this correspond with the graph that we drew? Well, let's go ahead and draw some more tick marks on our axis. 4 seconds, 8 seconds, 12 seconds. Well, here we have time equals 4 seconds, and where is buoy B? It's at equilibrium, and that does correspond with the graph that we drew. This is a graph that shows the position of B, or the position displacement of B versus time. It's always at position x equals 18 meters. It won't move left or right from that. We can draw an equation, or write an equation describing this graph. All we have to do is take this equation and plug in the position. So this equation is y equals 2 cosine 2 pi over 24 times the position is 18 plus 2 pi over 16 times time minus pi over 2. This again is 36 over 24. And we get y equals 2 cosine 3 pi over 2 plus 2 pi over 16 times time minus pi over 2. Now I can do 3 pi over 2 minus pi over 2 to simplify this a little bit further. What we get is y is equal to 2 cosine 2 pi over 16 times time plus pi. That is our equation to describe the position or the displacement of buoy B versus time.